Hello all, and welcome again to this comprehensive tutorial on fine-tuning large language models, LLMs in short. Fine-tuning allows us to adopt a pre-trained model to a specific task or domain or a dataset, unlocking its full potential with minimal computational cost. In this guide or tutorial, we will explore different fine-tuning techniques, including full fine-tuning, LoRa and QLORA, enabling efficient customization of LLMs for real-world applications. So let's dive in. What is fine-tuning? By definition, we take a pre-trained model. When we say pre-trained model, here I am assuming a pre-trained LLM model, and we try to adapt it to a specific task by training it further on a smaller or domain specific dataset. For example, suppose we have a pre-trained model here. Now this pre-trained model can be anything. For simplicity, let's just say this pre-trained model here, it is a llama model. It is a llama model, and on top of this model, if I want to train a specific data here, now this data here can be of a particular hotel. Suppose I own a hotel here. Now I don't want to disclose this data here to any outside world. In that case, I will take this llama model and I will train or fine tune this llama model on top of this data. So my new fine-tuned model will have this knowledge base embedded into it. This is a quick overall holistic view of what fine-tuning looks like. Now this fine-tuning here, we can do it in multiple ways. We have full fine-tuning, we can do parameterized fine-tuning, we can do fine-tuning with the use of adapters. In this module, we are going to look at how we can do this fine tuning in a more efficient way using LoRa, which is low rank adaptation, and using QLORA, which is quantized low rank adaptation. So let's move forward. Let us look at some major fine tuning techniques available to our use. Two of the major techniques are full fine tuning and parameterized efficient fine tuning. So in full fine tuning, we take all the model parameters and we try to update them, requiring significant computational resources. So this is, if we are trying to do full fine tuning, we need a lot of GPUs, which is normally not possible for a normal consumer base. So for people like us or developer like us, they don't own really heavy GPUs. So full fine tuning goes out of the picture. Now to our rescue, we have PEFT, in which what we try to do, if there is a big matrix in front of us, which is denoted by W, suppose this W has a lot of weights. This weight is nothing but the weight of a deep neural network. So at the end of the day, an LLM is a deep neural network, a very deep neural network with a lot of weights inside it. This matrix suppose has all the weights. So in PEFT, what we try to do, instead of trying to update all of the weights, we take a small subset of the weights, W dash, and we will try to update this only. So this is parameterized efficient fine tuning. By definition, only a subset of parameters are trained, making it computationally efficient. This brings us to the most important and efficient PEFT technique, which is LoRa. Now, before we try to understand LoRa in detail, there are two important concepts which we need to understand. So, two important concepts are what is the rank of a matrix and how do we calculate this rank? What is this rank? And second one is what is the decomposition of a matrix? Pardon for my writing. So, these two concepts are very important before we try to understand LoRa in detail. So, let's first explore what is the rank of a matrix. The rank of a matrix is nothing but how many rows or columns are linearly independent. Basically, it represents the dimensionality of the vector space spanned by the matrix rows or columns. This will become more clear through this example here. Suppose we have two matrices here. I am calling it matrix A and I am calling it matrix B. The rank of matrix A is 1 and the rank of matrix B is 3. Why? Let's try to understand that. So if you look in matrix A, we have two rows. So let's say we have R1 here and we have R2 here. If you look closely, R2 can be presented by R1. Let's see how. So in R1 we have 1, 2 and 3. In R2, if we multiply R1 by 3, it will become 3. If we multiply 2 by 3 again, it will become 3. And if we multiply 3 by 3 again, it will become 9. So eventually it becomes 3, 6, 9. So R2 here can be represented using R1. So it's not linearly independent. That's why we say only one row here is linearly independent. That's why the rank here is 1. While in this case, in matrix B, all the columns and rows are linearly independent. None of them can be represented using the other. This is a basic definition of what is the rank of a matrix. Another example could be, let's suppose I have a matrix C, which is 1, 2, 3, and 4. So this is my matrix here. Now this matrix here, the rank of this matrix would be how much? It would be 2, because none of the rows or columns can be represented through each other and they are linearly independent. This is a basic definition of what a rank looks like. There are many algebraic formula through which you can calculate the rank of a matrix, but for simplicity, we will be using all the libraries available to our disposal to calculate the rank of a matrix. Now let's move forward and let's try to understand what is a matrix decomposition. Matrix decomposition. So matrix decomposition is the process of breaking down a matrix into simpler matrices that are easier to analyze, compute, or interpret. It is widely used in machine learning algorithms, computer vision, and specifically in LLM fine tunings, specifically in LoRA, of course. And this is also used for a lot of dimension reduction problems. So if at all you are in a situation where you want to reduce the dimension, this should be your go-to approach in certain cases. So by definition, this is the process of breaking down matrix into a product of simpler matrices. It's really simple. Suppose we have a big matrix in front of us. Suppose this is a 4 cross 4 matrix, and we want to split this matrix. The way we split this matrix here, if you look at here, so this matrix name is W. We will try to split it into two matrix A and matrix B. The way we split this A and B is that whenever we multiply or we do a dot product of these two matrices, this is the result. So this is the actual technique behind LoRa as well. So we take, instead of modifying the whole weight, we decompose the weight matrix into two small matrices and we try to do operation on them. And at the end of the operation, we just update the weights by multiplying them. This seems pretty easy. So if we have this W1 here, let's suppose this is W1, and we try to decompose. The way we decompose is that the dimension of this is 4 cross 1 and the dimension of this is 1 cross 4. So whenever we do a multiplication of this 4 cross 1 and 1 cross 4, the output would be 4 cross 4, which is eventually this matrix. That's super easy, isn't it? So now let's move forward now to understand what is LoRa. LoRa is a parameter efficient fine-tuning method. So in full fine-tuning method, what we do, we try to update all the weights inside the model. Instead, in LoRa, what we try to do, we try to inject a small trainable low rank matrices, like we have seen how we decompose the matrix. Now we decompose that matrix and we try to create a low rank matrix out of it, and we inject them into specific layers. For example, in transformers architecture, you must have seen we have three layers. We have A, Q, and V. So instead of directly working on all these matrices, we create a low rank matrix of these and we try to work on them. This enables efficient adaptation while keeping the pre-trained model weights frozen. It's really memory efficient and it's fast as well. The research paper here clearly indicates all the techniques used in LoRa, clearly tells us how we decompose the pre-trained weights into low rank matrix A and B here, which is clearly visible here. So this is a very detailed research paper of how LoRa can be used and how LoRa is compared to other fine-tuning techniques available to our disposal. Now let's come back to our slides here. Okay, so we have seen what is LoRa. Whatever I am portraying here is directly taken from the research paper. So now let's move forward and try to understand LoRa in a bit mathematical way. This is the original weight here. This is from the LLM itself. Suppose like in earlier example, we must have seen we have an llama model. On top of this llama model, I want to train a data from my hotel. So this is my hotel and I have some data from this hotel, and I want this llama model to have this data embedded in here. And if I ask any question to this llama model, suppose I give any query here, let's represent query with Q. Now this model should answer me based on this data context here, this new data context here. So to do this fine tuning, we are going to apply LoRa here as we are progressing further. So we are going to use LoRa here. Now, how do we use LoRa and what is LoRa? I have explained. Now in this, we will try to understand a mathematical representation of what we do inside LoRa. So this is the original weight we are having. This is the original weight from llama model. So let's represent it here. And this is a delta W. This is the new weight which we will be adding into this original weight. So, and an ideal situation, this is W new. So this is my W new, this is my W original, and this is the delta W which we will be creating. Now on this delta W, we are not directly working on this delta W. We will decompose this delta W into A and B. How do we decompose? Here we apply the matrix decomposition. So as we have seen earlier, how we decompose the matrix into two matrix. So it's a high rank matrix which will be decomposed into two matrix here, matrix A and matrix B. Now all the operations will be done only on this matrix, matrix A and B, and at the end of operation we will just add all of this and we will create W new. Super easy, isn't it? Now let me try to give you, once we create the new delta W, or suppose delta W is equal to A, let me just delete it. It's messing it up here. All right. So we have this delta W, which is equal to A and B. This delta W we will calculate for all the layers inside the transformer architecture. So if you remember, inside this transformer, this is how we calculate the attention. We apply a softmax on QKT under root dk by V. So Q represents the queries, K represents the keys, and V represents the values. So here what we try to do in process of LoRa, we add modifications to WQ, WK, and WV with the help of matrix decomposition. Now during inference, the modified values are WQ plus A and B, and for K it would be WK plus A and B. Here A and B for all the layers will be different. For example, let's represent this A and B by AQ and BQ, and this will be represented by AK and BK. Now similarly it will be for WB. This is the WV here, and this is the WK here, and this is the WQ here. So WV will be A of V and B of V. Now this multiplication eventually will result into delta W, delta V. So this is basically how we decompose the matrix, and on which particular attention layer we add this delta W. Now during the inference, the modified values will be used. This makes fine tuning highly efficient while preserving the model's pre-trained knowledge. Now let me give you a more mathematical representation of how efficient it has become the moment we have introduced the matrix decomposition. And let me also tell you what is the significance of rank here. So let's suppose we have a matrix W which is member of a real number with D is equal to 4096. Basically D and K here are the dimension of a matrix. So suppose this is a big matrix in front of me with a value of D and K. So D here is 4096 and K again is same 4096. So total number of trainable parameters for this matrix, if it is, this is the actual LLM model matrix. So I am using llama 2 here, and let me just name it llama. this is the weight matrix of llama 2, the whole model. If at all I'm going to train, or if I'm going to modify all the weights inside this, total trainable parameters I'm having here is this, which is 16 million approximately. It's super easy to calculate. We just multiply d and k and we get total trainable parameters. Now let's assume we are trying to do LoRa on top of it. Let's using this technique, LoRa technique. Let's see how it goes. So let's suppose we are going to use rank 4 here, and for A, the matrix A, which is this big matrix decomposed into two matrix, matrix A and matrix B. So matrix A is, let me change the color. So matrix A is this, sorry, not this. Let me just remove it. There you go. So matrix A is this and matrix B is this here. So matrix A will be represented by, so this is the, this is the dimension of the matrix. Dimension of the matrix will be 4096. So 4096 into 4, and dimension of matrix B is 4 into 4096. Here 4 represents the rank. That's where the ranks come in very handy. So if you will increase the rank, the total number of trainable parameters will increase significantly. This is very important for you to understand. Let me again repeat it for you, and let me first delete this so that we don't mess it up. I'm again reiterating what we are trying to do here. So we have this bigger matrix here, W. So if we use or we try to update all the weights inside this matrix, total number of trainable parameters which we are having is 16.7 million here. This is now using LoRa. What we'll try to do, we will try to decompose this big matrix into two matrix, which is here matrix A and matrix B. You see here, and we will be using rank 4. Now we try to decompose this matrix. So once we decompose a big matrix, we are trying to decompose into two matrix, matrix A and B with the dimension of 4096 cross 4, and matrix B with the dimension of 4 cross 4096, where R is the rank of the matrix. So if we increase the rank, the total number of trainable parameters increases significantly. So here total number of trainable parameters, how much it is? It's 32k. So it's from 16.7 million, it has reduced to 32. The factor through which is it has reduced its 10 to the power 3, almost 10 to the power 3. So this is how efficient LoRa becomes. So if you see it from a more mathematical perspective, things become super clear. Now if at all you have to train using full fine tuning, you will really need a very heavy GPU. But imagine training this using rank 4 and this decomposition. You can train it using a normal laptop. I have tried to train it in my Mac M2 machine. It has performed pretty well, but at certain times it crashes. Make sure you close all other applications. It takes a lot of VRAM if you are trying to train on your local MacBook. So this is a quick overview of how important LoRa is and what is the mathematical representation of LoRa. Amazing feature of LoRa is that it can be combined with other fine-tuning techniques like adapter, quantization, and etc. So if we combine LoRa with quantization, it becomes QLORA. So it becomes quantized low rank adaptation. QLORA is an extension of LoRa that further reduces the memory uses by quantizing the base model to 4-bit. This is really important to understand. In quantization, what we do, if there is a big number, suppose this number is taking 8-bit of a space, 8 byte, let's say it is taking 8 byte of space, we quantize it and we say in next form, you will take only 1 byte of a space. This is nothing but quantization. A big model, suppose this model is of 1 GB. By quantization, we can convert it into hardly 200 MB model. Now let me try to explain this quantization technique in bit more detail to you. You must have used float 32 and 16-bit to store variables. So in Python or any other programming language of your choice, we always try to use float 32 or 16 based on the scenarios. Here, let me try to give you a real-time scenario. What happens when you actually use 32 and what happens when you actually use float 16 data type. So if you directly specify float 32, this is the data which will be going to stored in your memory. So if you are saying I'm going to use float 32, the value would be 1.234567 and 9. This will be the whole value which will be stored in the system. On the contrary, if you're trying to use float 16, this would be 1.235. So if we are going from float 32 to 16 bit, we are losing precision here. So in quantization, when we go from float 32 to 16 bit, we take a call that it's okay for me to lose the precision, but there are certain cases where we don't want to lose this precision. Now, why do this going from float 32 to 16 bit is important? For that, we need to understand the memory allocation for this. So if we are using float 32, the memory allocation is 32 bit. If we are using float 16 here, the memory allocation is 16 bit. That's too less. Now this number may look really small to you right now, but think it like in terms of very big model. We have 1 GB of model. If we try to do quantization on top of it, the resultant model would be 500 MB, which will be 50% reduction in memory space. Now let me give you a more detailed explanation on how internally it works. So let me just delete it so that it does not mess up with our. All right. So here, if we are going to use a 32 bit, this is 32 bit. So if you are going to use 32 bit, the first bit will be for the sign and remaining 8 bit will be for exponent, and 23 bit will contain the fraction of that number. Similarly, if we are trying to use 16 bit, if we convert 32 bit into 16 bit here, eventually first will contain the sign and next 5 bits will contain the exponent, and again next 10 bits will contain the fraction details. But you see, it takes very less memory space, 50% reduction in memory space. This same applies to the QLORA technique which we are trying to use here. So in LoRa, what we do, we decompose a big matrix. Suppose this is a big matrix in front of us, matrix A and B. These are low rank matrix. It's very important that in LoRa we do low rank adaptation. So big matrix. So this is a big matrix converted into two small, not converted, decomposed into two small matrix, matrix A and matrix B. Now suppose this matrix are low rank matrix. On top of it, if we apply quantization, so quantization would be, if we apply quantization on all of it, on the data types which has been used inside to store the weights. First, the weight was taking 32 bit. Next, if we apply quantization, let's say it is taking 4 bit only. 32 bit to 4 bit. You see, by applying quantization, we have reduced the memory space. So that's why it has become quantized low rank adaptation. It's very simple to understand. Let me delete it again and explain it to you. LoRa, we have understand it's low rank adaptation, big matrix converted into small matrix. Now eventually these small matrix will contain weights W and W. These weights will be nothing but floating point numbers 1.24567. If we apply quantization on this as well, it will become more memory efficient. So after applying quantization, the new weights would be the new storing weights would be, that's how we will store it, would be 1.24. We are losing the precision, but we are becoming more memory efficient. It's really important when we try to do QLORA or LoRa, because there are certain cases where we don't want to lose the precision. We want to keep the precision. So based on the scenario and based on the data type and use case we are dealing with, we try to apply quantization and we try to do apply LoRa as well. So LoRa with quantization becomes quantized low rank adaptation. So this is an overall summary and holistic view of how LoRa works and what is the internal mechanism inside that LoRa. If we look at the research paper, there is a lot more to discover on this LoRa. The research paper has provided us with tables of how efficient this LoRa is with related to other techniques, like we have adapter techniques as well. The good news is that we can apply adapter techniques to LoRa as well. So we can combine LoRa with adapter and suffix techniques to see how it works. But the most efficient way we use LoRa is with QLORA, the quantized low rank adaptation technique. I hope you have learned something in this video. See you in next part.